So we now have all the tools we need to discuss the general method of solving any kind of linear systems of equations. So let's consider a general n by m system ax equal to b. N equations and m unknowns. To solve this system, we do the following. First of all, we create the augmented matrix C, which will be n by m plus 1. Then, once we have the augmented matrix C, we find the reduced row echelon form of C. We then know that this reduced row echelon form is an augmented matrix of an equivalent system to the one we started with. The advantage being that this reduced row echelon form represents a system which is much simpler than the one we started with. So for the next step, we recreate the system from this new reduced row echelon form. And this will be so simple that we can immediately solve the system. And when we say solve, we mean that we can figure out if the system has a unique solution and figure out what that is. We can figure out if it has no solution at all, or we may deduce that it has an infinite number of solutions. Here are some simple examples. Let's say we have this system, a 3 by 2 system, 3 equations and 2 unknowns. Just simply construct the coefficient matrix A. You have the B vector, combine them into the augmented matrix C. Find the reduced row echelon form of C. For this fairly simple example, it's not that hard to do it by hand, or you can use R to find the reduced row echelon form. In any case, the reduced row echelon form is this. This is an augmented matrix of an equivalent system. Going backwards, we see that this augmented matrix represents the following system. For this particular system, there's nothing more for us to do. We immediately see that it has a unique solution. And since the first system of equations and the final one are equivalent, we know that the first one also has a unique solution, x1 equal to 1 and x2 equal to minus 1. Let's consider a couple of other examples. First, let's consider x1 plus x2 equal to 0, x1 plus x2 equal to 1. It's quite clear that this system can have no solution. x1 plus x2 cannot both be 0 and 1. But it's still a useful example to see what the result will be in terms of our solution strategy. In this case, our coefficient matrix is 1, 1, 1, 1. Our B is 0, 1. Our augmented matrix is 1, 1, 1, 1, 0, 1, like this. And the reduced row echelon form of this matrix is 1, 1, 0, 0, 0, 1. Simply subtract the first row from the second. And this augmented matrix represents x1 plus x2 equal to 0 and 0 equal to 1. That is the second row. It really says 0 times x1 plus 0 times x2 should be equal to 1. And that, of course, is impossible. There are no x1 and x2 such that 0 times x1 plus 0 times x2, which is always 0, that cannot be equal to 1. There is a general lesson from this example. If you look at the final row of this augmented matrix, you see that it's a 0 row, with the exception of the final element, which is non-zero. Well, if you find such a row in an augmented matrix, the system simply cannot have a solution, because such a row always will translate into something saying 0 is equal to something which is not 0, and that's impossible. Let's consider another interesting example. x1 plus x2 equal to 1, x1 plus x2 equal to 1. I have two equations and they actually say the same thing. meaning that the second equation is really redundant. And just looking at the first equation, we see that we have an infinite number of solutions. In this case, the augmented matrix is 1, 1, 1, 1, 1, 1. And the reduced row echelon form of this matrix is 1, 1, 1, 0, 0, 0. Again, simply subtract the first row from the second. And this augmented matrix represents the system x1 plus x2 equal to 1 and 0 equal to 0. 0 equal to 0 is always true. It tells us nothing, so we can actually remove that. And we see that the second equation really is redundant and that the system has an infinite number of solutions. Again, there is some useful information here. If you find a zero row, like this one, in an augmented matrix C, we know that you can simply remove that row because all it says is that 0 is equal to 0. So you can actually move to an augmented matrix which just looks like this. When we have a linear system of equations, it's quite common that we're actually only interested in the question of whether the system has a unique solution, no solution, or an infinite number of solutions. We might not be interested in what the actual solution is. So let's look at the strategy for determining the number of solutions of a system. Again, consider this n by m system, ax equal to b. Now, if you are interested in figuring out the number of solutions to a system, you actually don't have to go all the way and find the reduced row echelon form of C. It turns out that it is then enough to just do the row echelon form of C. When we try to find the row echelon form of C, we are basically removing elements in the bottom left part of the augmented matrix. Once we have it in row echelon form, we may continue to the reduced row echelon form. And then we try to remove elements in the top right part of the matrix. So in this case, let C prime just be the row echelon form. Of course, it doesn't hurt if C prime is the reduced row echelon form. Any matrix which is in reduced row echelon form is also in row echelon form. If you, in this matrix, find a row which is a zero row, with the exception of the final element in the last column, if that is non-zero, then we know from the discussion before that the system can have no solution because that row will translate into something like 0 is equal to 1. So the first thing we can do is to look for such a row. If you find such a row in C prime, the system is inconsistent and there is no reason to continue. So let's say that the augmented matrix passes this test. It doesn't have any rows with this property. The next step is to look for zero rows. We know that we can remove such rows because they tell us nothing except that 0 is equal to 0. Once you have removed the zero rows, if there are any, remove the final column of the augmented matrix. If you are left with an upper triangular matrix with non-zero elements on the diagonal, well, then you know that the system will have a unique solution. So let's review this. The system will have a unique solution if once you have removed zero rows, which tells you nothing, and the last column, you're left with an upper triangular matrix with non-zero diagonal. It's actually not that hard to understand why the system must have a unique solution in this particular case. Let's look at this example. x1 plus x2 equal to 2 and x1 minus x2 equal to 0. The augmented matrix is 1, 1, 2, 1, minus 1, 0, And the row echelon form is 1, 1, 2, 0, minus 2, minus 2. If I remove the last column of this matrix, I get 1, 1, 0, minus 2. And this matrix is square. It is upper triangular. And we see that the diagonal elements are non-zero. So this system must have a unique solution. Why? Well, if I translate this C prime into its system of equations, it says x1 plus x2 equal to 2, and it says minus 2x2 equal to minus 2. If you look at this system, you see that the last equation, we can use that to solve for x2. We see that x2 is equal to 1. Once I have solved for x2 from the last equation, I can use that solution in the first equation. If I know that this is equal to 1, I can solve the first equation and find that x1 must also be equal to 1. But this idea always works. If I have an augmented matrix C, which is in row echelon form, and it looks like this, except for the final column, the rest of it is in upper triangular form. That means that I have a diagonal here. All the elements below the diagonal will be 0. And up here I can have elements. I also know that every element along the diagonal is non-zero. Well, in this case, we see that the last row has something like 6x6 equal to 4, for example. The important part being that there is only one x variable because everything else here is 0. So I can always use the last equation to solve for x6. Then move up to the row above it. This row has something like 4x5 plus something like 3x6 equal to whatever, 9. Once I have solved for x6, you see that you can solve for x5. That is, you can always use this iterative procedure to go up along the rows and solve for each x variable. And since the diagonal is non-zero, I know that the coefficient in front of, for example, x4 in this row, the coefficient in front of x4 will not be equal to 0. And since the coefficient in front of x4 is not equal to 0, I will be able to solve for x4 once I've solved for x5 and x6. So this is the reason why we must have a unique solution if the row echelon form of the augmented matrix has this particular form. A simple iterative argument solving sequentially for each of the x variables leads us to this conclusion. Finally, if this does not happen, then we will know for sure that the system has an infinite number of solutions. Let's say, for example, that our augmented matrix looks like this. I have B to the right. Let's say I have a non-zero element here represented by a cross. Then some element here, which may or may not be 0, and some element here. On the second row, I have a 0, 0, a non-zero element here, and any element here. In this particular case, if I remove the last column, I'm left with something like x dot dot 0, 0, x. Well, this matrix is 2 by 3, so it cannot possibly be upper triangular. It's only square matrices that can be upper triangular. This system must have an infinite number of solutions. I can use the final row to find a solution for x3, but if I try this iterative procedure discussed previously and I put x3 into the first equation, we see that we do not have enough information to solve for x1 and x2, implying that the system will have an infinite number of solutions. From this discussion, we can actually realize also that if you have a system which is under determined, that is, it has less equations than variables, then it's absolutely impossible for that system to have a unique solution. The reason is simply that for an underdetermined system, the number of rows of the augmented matrix will always be less than the number of columns, even once you've removed the final column. But then the fourth bullet point in this slide cannot be fulfilled. If you remove the final column, it's completely impossible that you end up with a matrix which is upper triangular, because the remaining matrix simply cannot be square. For an over-determined system, it is possible that the system has a unique solution. And this is really due to the fact that we first remove 0 rows. And when we remove 0 rows in an overdetermined system, you might actually remove exactly the number of rows necessary for the remaining matrix to be square and have a non-zero diagonal. So here are some examples of determining the number of solutions. So keep in mind the strategy, create the augmented matrix, make it into row echelon form or reduced row echelon form if you like. Begin by looking for a 0 row with a non-zero element as its final element. If you find such a row, the game is over, the system is inconsistent. Like this one, the last row is such a violating row. If you pass this test, remove any potential 0 rows, remove the last column, and look at the remaining matrix. Here are 2 examples. In the first one, there are no 0 rows, nothing to remove. If I remove the final column, I end up with a 3 by 3 matrix, upper triangular, and non-zero diagonal. I can use an iterative procedure to first solve for x3 using the last equation, plugging in the solution for x3 in the second equation, solving for x2, then plugging in the solution for x2 and x3 into the first equation, solving for x1. And in the second example, first we have to remove the last row, and once we've done that, I'm left with a 2 by 2 matrix which satisfy these criteria. Finally, here are examples of systems with an infinite number of solutions. In the first case, I have a 2 by 3 matrix once I remove the last column, cannot be upper triangular. And in the second case, I have to begin by removing the final row. After removing the final column, I'm left again with a 2 by 3 matrix, which cannot be upper triangular. A common procedure used by many to determine the number of solutions is to enclose the leading elements as discussed before. In this first case, it would look like this once I enclose the leading element, but in the one below, it would look like this. There is a big difference between these 2 examples. In the first case, I always go down, right, down, right, down, right. In the second case, I go down and then I go right 2 times before I go down again. Well, if you have to go to the right 2 times, then you know that the system must have an infinite number of solutions. At least if you have checked this first condition first to see that it's actually consistent. Same thing goes for these second examples. I go down, right, down, right. Here I go down, right, right. So it's again an infinite number of solutions. For systems that do have an infinite number of solutions, there are concepts called free and leading variables. So let's take a look at that. Remember that the first non-zero element of a row is called the leading coefficient. So in this example, we have a leading coefficient here and here. That is, we have a leading coefficient in column 1 and in column 3, but we have no leading coefficient in column 2 because we make this double step to the right here. If I have a leading coefficient in column 1 and column 3, then I simply say that x1 and x3 are lead or leading variables. While, since I have no leading coefficient in column 2, we say that x2 is a free variable. For example, if you have a system which has a unique solution, if you look at the stairs, it's always down, right, down, right, down, right. That means that you must have a leading coefficient in every column. So for a unique solution, you know that there are no free variables. However, if you have an infinite number of solutions, like these two examples, then you know that you must have at least one free variable. So to summarize, if there is a leading coefficient in column J, where J goes from 1 to K, then the corresponding X variable, Xj, is called a lead variable. Otherwise, it's a free variable. And it's only systems with an infinite number of solutions that have free variables. The example we looked at was this one. x1 and x3 are lead variables while x2 is free. The point of identifying lead and free variables is then the following. You can always write a solution for all the lead variables in terms of the free variables. To illustrate this, we again look at this example. The corresponding system is, keep in mind, x1 and x3 are lead variables, while x2 is a free variable. So I should find the solution of x1 and x3 in terms of x2. And in this case, it's quite simple. If I plug x3 equal to minus 2 into the first equation, x1 is equal to minus 3 minus 2x2. I have expressed the solution of x1 and x3 on the left-hand side with x2 on the right-hand side. So by free, we simply mean that you can pick x2 to be anything. For example, you can pick x2 to be 0. Well, in that case, x3 is always minus 2, while x1 in that case will be minus 3. Picking another value of x2 will give you another solution for x1. Finally, let's take a look at a balanced system. Remember, a balanced system is a system where you have the same number of equations as unknown variables. So we have an n by n system. For a balanced system, we have a special result, namely the following. If I want to figure out if a balanced system has a unique solution, I don't have to go through the procedure just described. A balanced system will have a unique solution if and only if the matrix A is invertible. We'll prove this in an exercise later on. If A is invertible, then it's also very simple to describe what the solution is, namely A inverse times B. If you plug this solution into the system, it says A times X or A times A inverse times B. And we know that A times A inverse is equal to the identity matrix if A is invertible, and that proves that AX is equal to B. If A is not invertible, then it's not possible to say if the system has no solution or an infinite number of solutions. To figure out which case it is, you have to go through the procedure just described. Again, keep in mind that this only works for balanced systems. If you have an unbalanced system, we cannot even talk about the inverse of A. So for such a case, you have to create the augmented matrix, do row echelon form, and so on.